All right, we are actually going to approximate the area under a curve. We're going to use a Riemann sum to do it. We're going to add up a bunch of areas of rectangles to do it. So we want to approximate the area under f of x equals e to the x over 2, which is going to look something like that, some kind of exponential growth. And we want to go from a equals 2 to a to b equals 5. So we want to find or approximate this area here, and we're going to do it with rectangles. So, we can just draw these rectangles. Drawing the rectangles is not part of this problem, but I think it's still good since this is new to illustrate what we're doing. So we add up the areas of those 6 rectangles, and we get an approximation to the area under the curve. And if we used more rectangles, we'd get a better approximation. But we're going to use 6 rectangles and get our approximation. Now we know that the total area is approximately equal to the sum from k equals 1 to 6 of f of x sub k times delta x. F of x sub k is the height of each of these rectangles, and delta x is the width of each rectangle. So this is a height times a width, which gives us an area of a rectangle. Then we add the areas of the 6 rectangles together to get our approximation. I should have said approximately equal to here instead of equal to. So A is approximately equal to the areas of these 6 rectangles added together. So that is what we're going to do. This is a right-hand sum. If we wanted a left hand, then it would be a sum from k equals 0 to 5 of f of x sub k times delta x. So that's the difference between the right-hand sum and the left-hand sum. When we get down to it, it's a question of how we measure the height, or where we measure the height of our rectangle, from the left end point of the interval or the right end point of the interval. So what do we need in order to use this formula? We need delta x, and we need to know where x sub k is. So delta x, our general formula is just b minus a divided by n. So for us here, that's 5 minus 2 divided by 6. 6 rectangles, and the interval is 2 to 5. So that is 3/6 or 1/2. So our delta x equals 1/2. Now our x sub k locations, that is the location of each of these rectangles. The x sub k locations are given by a plus k times delta x. So for us, that's 2 plus 1/2 k, and we just list them out. X sub 0, if we put in a k equals 0 right here, we just get 2. So x sub 0 is our starting point, 2, which makes sense. Our interval starts at 2. X sub 1 is 2 plus 1/2, so 5/2. X sub 2 is 5/2 plus 1/2, so that's 3. X sub 3 is 3.5. X sub 4 is 3.5 plus another half, which is 4. X sub 5 is 4 plus 1/2, so that's 4.5 or 9/2, and then x sub 6 gets us to 5, the ending point of our interval. So here we have 7 points evenly spread, delta x of 1/2. 7 points creates 6 intervals or 6 rectangles. So those are the points where we have to evaluate the function in order to get a height of a rectangle. With all of this, we can put it all together now. We can say the area is approximately, remember it's the sum from k equals 1 to 6 of f of x sub k times delta x. So for us, that is f of 5/2 times 1/2 plus f of 3 times 1/2 plus f of 7/2 times 1/2 plus f of 4 times 1/2 plus f of 9/2 times 1/2 plus f of 5 times 1/2. We could factor the 1/2 out of this if we prefer. That's just fine. We can do that. But there it is. Now, finally, if we wanted to actually compute what this approximation is, we know what f of x is. F of x, remember, f f of x is e to the x over 2. So we can actually plug this in now. Notice we did start at 5 halves and not at 2 because our summation started at 1 and x of 1 is 5 halves. If we had been doing the left-hand sum instead, we would have started, for the left-hand sum, we would have started at 0. We would have had an f of 2 up to an f of 9 halves. So anyway, back to what we're doing. F of 5 halves is e to the 5 fourths. So we have e to the 5 fourths, and I am going to go ahead and factor out the 1/2 to make this a little bit less writing for me. So each of those terms has a 1/2, so we'll factor that out. Plus f of 3 is e to the 3 halves plus e to the 7 fourths plus e to the 4 halves, which is 2, plus e to the 9 fourths plus e to the 5 halves. There I've got my 1, 2, 3, 4, 5, 6 rectangle heights, all times the same width of 1/2. And that is our approximation. At this point, I can't do anything except go to a calculator or a computer to add these numbers together and see what the actual decimal approximation is. But that's our Riemann sum approximation. You can see why we don't do this by hand. We have computers or calculators do this for us because it's tedious to do it by hand, and we need a calculator at the end anyway to get our answer. But I think it is good to do it, write it out a few times like this to get familiar with the process and an understanding of what we're doing and what's going on with these Riemann sum approximations to the area under a curve. So there it is. That's our right-hand sum or right-hand Riemann sum for this particular problem.